Hey everybody, I hope you're doing great today. Let's finally jump into Bayes' rules. So the idea with Bayes' rules, it's directly going to be building off of what we looked at last time with conditional probability. So remember, conditional probability is all about how does our confidence in something change based on new information. So let's dive in with a particular example. Suppose you start off thinking there's a 20% chance that you're currently sick, right? Something is going around, maybe 20% of your community has it. Either way, you start off thinking 20% of chance I'm sick right now. You're not sure, but you're also not sure you're healthy. So you decide to take a test, and just like with any test, there's a chance that it tells you you're sick even if you're not, right? So if you are sick, there's a 70% chance it tests positive, but there's also a 30% chance even if you're sick, it doesn't tell you you're sick, right? And if you're not sick, there's still a 10% chance you test positive, right? Even healthy people will have a test that says, yes, you're sick 10% of the time, right? And of course, these numbers differ by the test. This is what makes a test better or worse, is what these numbers actually are. But every single test you'll ever take in medicine or really wherever is going to have these sorts of things involved. So anytime you take a pregnancy test, there's a chance it tells you you're pregnant even when you're not. There's a chance it tells you you're not pregnant even when you are. So our question really is, so how much should these positive or negative tests affect our confidence? They're not guarantees, right? If I get a positive test here, I'm not guaranteed to believe that I'm sick because I don't know if I'm just one of the healthy people that still just happened to get a positive test. So our question is really, if we started off at 20%, how should we change our confidence? Right? How should we adjust our confidence now? It shouldn't be at 100% because, again, it's not a guarantee. But where should we put it? 50%? 60%? Right? Like, where should we put that new confidence? So we can get more general and we can be thinking about this just in terms of our hypothesis and our evidence. How much does our evidence increase or decrease our confidence in the hypothesis? If I start off 20% confident in my hypothesis, and I know seeing this evidence is 70% likely to occur if the hypothesis was right, but it's 10% likely to happen if the hypothesis was wrong, then how should I adjust my confidence in this hypothesis? So a way of thinking about this is in terms of just these three numbers, and we're trying to get to this fourth. If I start off thinking that the hypothesis has a 0.2 chance of being likely, but seeing the evidence, if my hypothesis was in fact correct, would be 0.7, whereas seeing my evidence if my hypothesis were not correct would be 0.1, then how confident should I be once I see my evidence? How confident should I be in my hypothesis once I see that my evidence did actually happen? So a way to think about this is really that we're starting off with P of E given H, right? What's the probability that I test positive given that I am sick? And what I'm trying to figure out is, okay, what is the probability that I'm sick given that I test positive? So that's the real question that we're going to be diving into, is really how do we swap these conditional probabilities? How do we find the probability that your hypothesis is true given that you've seen evidence from your knowledge that your evidence is true given that you've seen the hypothesis? So the real question is, how do we go from something like this, right, where we know how likely it is to see the evidence given some hypothesis, this is what we call a true positive rate, to something like this, where we're asking how likely is the hypothesis given that we've seen the evidence. Okay, so this could be a bit confusing the first time around, and I think one of the best ways to learn this is by looking at it in three different ways. So that's what we're going to turn to next. Each one of these is going to be justifying the exact same thing, which is this right here. This is called Bayes' rule. And the idea is Bayes' rule allows us to take something like the probability of your evidence given your hypothesis and determine the probability of your hypothesis given your evidence. Some of these explanations are going to be more intuitive to some of you versus others. And that's the reason why I'm giving you all three of these, so that hopefully at least one of these will latch on and you can see what's going on in Bayes' rule. When it really comes down to it, after we've talked about these, actually doing the problems becomes really straightforward. The question is just your intuition leading into that. So let's get started. The first way I want to show you how to think about Bayes' rule is really just straight from the definitions. That we're not doing anything mystical or magical. This is just based on the definitions. Bayes' rule falls out. So if you're a particularly math-minded person, this might be the explanation for you. So the idea is if we start off with just the probability of H and E, as well as the probability of E and H, well, these are just the same thing, but both of them we can rewrite using the definition of conditional probability, right? The probability that H happens and E happens is just the probability that E happens, and then given that E has happened, what's the probability of H, right? But it's also another way of doing that. The exact same value is going to be the chance that H happens, and given that H happens, what's the probability of E, right? Both of these are going to tell us what is the probability that they both happen. So the idea is both of these are equal, so we can just set these two sides equal, right? The probability that H happens given that E happens times the probability that E has actually happened is just the same thing as the probability that E happens given that H has happened times the probability of H has happened. This isn't supposed to be, right, super complicated right here. This is just two different ways of writing the same conjunctive probability. So all that Bayes' rule then is just dividing off the P of E here, right? We just get P of H given E, once we take off this P of E, is just P of E given H times P of H. And then we've just divided by the P of E. And that really is just Bayes' rule. So a lot of times when you see Bayes' rule written, you will see it in this form, where you just have your simple denominator down below. Now, the reason why I say it's simple is because we can also unpack this a little bit, and unpacking it can be pretty helpful. So let's think about what probability of E really is. So let's look at our whole sample space, and we can think about this as just divided into two regions. And we're just representing H and not H as just two regions of our probability space. Here's two different things that could happen. I could have H or I could have not H. I could also cut this up between E and not E. For any statement, I could just cut it up between all of the ones that make that thing happen and all of the ones that don't make that thing happen, right? This is what we meant by complements way back when, a couple of videos ago. If I want to think about this as just four separate regions then, right, I can break it up into, okay, well, there's the part where I have H and E. That's this top part up here, right? I have the E part and it's intersecting with the H part. But then there's the part where I have H, but it's in the not E side. And then I have the not H part with the not E, right? And then I have the not H with the E. So, right, the idea is I'm just breaking up my space into the four possible combinations. There's the place where I have H and E, the place where I have H but not E, the place where I don't have H but I do have E, and the place where I don't have either one of them. Then, what we need to notice is just that these two pieces, these two green shaded pieces here, those add up to the entire E piece, right? Because, that's the point. We have the place where E is true with H, and we have the place where E is true without H. And those are the two ways that E could happen. So really all that we're saying is the probability of E just equals the probability of E with H plus the probability of E without H. So the probability of E is just the probability of E and H plus the probability of E without H, right? Those are the two regions that together add up and create the entire E region. We can then take that denominator, right? Remember, the denominator right now in Bayes is just probability of E, and we could just work with that a little bit. Instead of doing the conjunctions, we can use those conditional parts, right? The probability of E and H is the probability of E given H times the probability that H happened. And then we could just do the same thing, right, with the other part. We can say the probability of E and not H is the probability of E given not H, and the likelihood that not H happened in the first place. And then we just substitute that into the bottom. And so oftentimes this is going to be how you see Bayes' rule. And really this is going to be most likely how you use Bayes' rule. It looks very complicated, but in reality, all that we're doing is we just plug in a handful of values, right? We just have the probability of E given H, the probability of H, and the probability of E given not H. Okay, so to see this break down a little bit more with regards to cards, right, we can be thinking about the same thing, right? I have H's and not H's in terms of a black card and a not black card, right? H would be the hypothesis is I'm drawing a black card of my deck. Not H would be well, you didn't get a black card out of your deck. And we could also ask, okay, well, so what if my evidence is that you got an ace, right? I drew an ace. There's the evidence outcomes, right? All of the aces, and then there's all of the not aces out here. And I know that all of my aces are just all of my black aces plus all of my red aces. All of the aces combined are just the aces split up into these two categories. That's all we're doing up here when we say that all of the probability of E is just split up into the probability of E with H and the probability of E without H. So this justifies the formula itself. And again, that's really what each of these demonstrations is after, is just justifying this formula. And after this will be an example where we can really see how do we actually do these Bayes rule problems. But it's going to turn out that doing the problems is actually much more the easy part. Understanding the why behind the rule, the why for what you're plugging all of these values into, is really the thing to wrap your head around. Once we actually get to doing the problem, you'll see it becomes really easy. We just plug in numbers and the answer comes out. So let's look at our next explanation for how this is supposed to work. And again, this isn't adding anything particularly new to the first one. I'm just saying this all in a different way to try to help you see the intuition going on in Bayes. And then we'll see, okay, how do we actually use this thing once we've got it? So let's return to our old friends, the truth tables. We could think about all four combinations of H and E. So just like always, there's the four possible worlds. There's the world where we have H and E. We have H without E. Where we don't have H, but we do have E. And where we don't have H and we don't have E at all. Right? And so if we think about this in terms of like the medical example above, right, we could think about this as, well, there's the world where I am sick and I test positive. The world where I am sick and I test negative. The world where I'm healthy and I test positive. And the world where I'm healthy and I test negative. So the idea is we're looking at all four possible ways that this world could go, right? We could have four different combinations of our hypothesis and evidence. And what we can do is, instead of attaching truth values to these, we'll attach the likelihood that each one of them are true. And all of these, of course, do add up to 1, right? That's the important thing from our second axiom. So what we want to find out is, if E were true, how does that influence? Does that make it more likely that H is true? And if so, how much? So our question is, if E does turn out to be true, how does that change the likelihood of H? How much more confident should we be in H if E turns out to be true? So we can start off by asking, okay, well, just how confident am I in H in the first place, right? And so what I'm going to do is I'm going to ask, well, there's two ways for H to be true, right? There's the first world and there's the second world. The probability of H is just the 0.2 from the first world plus the 0.3 from the second world means I am 50% confident that H is going to be true. If I look at all four possible worlds, I think there's 50% likelihood that I end up in one of the worlds where H is true, but there's a 50% likelihood that I end up in one of the worlds where H is false. And our question then is, if we learn that the evidence is true, how does that change our confidence? So I start off with a 50% confidence in H. We call this our prior. We say, all right, before anything else, I have a prior confidence of 50%. Now what we need to do is ask how things change if we find out that E is true. And to do this, we simply throw out the worlds where E is false. We're asking, okay, if we know that E is actually true, so we know we're not in world 2 or 4, we throw those away. And then all that we're going to do then is we're just going to ask, okay, what's the relative likelihood of the worlds that remain? So we know that we could only end up in world 1 or world 3. But we know it's not a 50-50. We know there's a greater chance of ending up in world 1 than of ending up in world 3. How much greater of a chance? To do this, we just take the ratio, right? We consider what's the total amount of probability pi that's left over, and how much of that belongs to world 1, or how much of that belongs to world 2. So whenever we do Bayes, the idea is we're ruling out some of the worlds and then just renormalizing or reportioning the amount of probability that's left. And we do it with respect to their relative sizes. Because world 1 is double as likely as world 3 right here, the same should happen when we condition. So that's why we get 0.2, the probability that H is true, divided by 0.2 plus 0.1, the probability that either H is false or it's true. So the idea is when we're trying to find out the probability of one of these worlds based on conditioning on E, right, based on ruling out that not E is false, then we take the probability of that world and we divide it by the total amount of probability pi that's left over, right? So finding the probability of H given E is taking, well, we have the probability of that world divided by the total. Or if we wanted to find out what's the probability of world 3, right? What's the probability of not H given E? Well, then we say, okay, well, we have the 0.1 of that world divided by the total, right? So the important thing to notice here is that this relationship is preserved. World 1 is double as likely as world 3. So all we're doing when we do a Bayes rule is we take out some of the worlds and then just readjust the likelihood in relation to the relative size of their likelihoods. That's all we're doing in Bayes' rule. We're just saying, okay, if we've learned something new and we've ruled out some of the probability space, let's just stretch the rest of the space in a way that still just captures what their original relationship was. So notice more generally what we have here. We have just the probability of H given E is just the probability of E and H. And that is just simply the probability of world 1, right? You have H and you have E. This was the only world where we had both of those things. And then we just divided that by the total of what was left over when we ruled out not E. And that is just the probability of E, right? That's just world 1 plus world 3. That's just the total amount that is E. But really, all that E is just world 1 and 3 again, right? So that's just E with H and E without H, right? E with H, and then E without H. And then we can just apply that definition of conditional probability, and we get to that Bayes rule that we had just over here. The idea is we started with confidence in H at 50%, right? So I was also 50% confident in not H. But then, when we conditioned on E, right, when we ruled out these worlds of the truth table, we said, oh, okay, now how much of the probability is left over, so to speak, for H and not H? And so when I conditioned on E, I saw that, oh, in the worlds where E is true, H is actually more likely than not H. Before we conditioned on E, H was not more likely than not H, right? They were both evenly likely. But by conditioning on E, this makes it so that H becomes more likely. So E shifts our confidence from being indifferent between H and not H to being more confident in H than in not H. This is what we mean when we say that something is evidence in favor of another thing, right? E in this case is in favor of H, and it is against not H. When I condition on E, when I add that new information, now I am more likely to believe that H is going to be true, and I am less likely to believe that not H is going to be true. So let's look at our final explanation of Bayes' rule. Again, this is going to be just saying the same things as the previous two, but I think this one is the most visual and potentially the most intuitive. Suppose you want to determine if you're sick and you decide to take a test. So our question is, how should you update your opinion based on the results of your test? So more specifically, suppose that 10% of people in your community are sick with some disease which doesn't really have any obvious symptoms. You just know that, generally speaking, 10% of the people in your community have this illness. So we have our hypothesis that I am sick, and we can think about the probability of our hypothesis, right? This is what we think of as our prior confidence that we're sick. our confidence at the start, right, should be something like 10%, right? We don't know anything else. We just know that we are one generic member of this community and 10% of us have this disease. So I'm not sure that I don't have it. I'm not sure that I do have it. I think there's a 10% likelihood that I have it. And then we can think about our evidence as receiving a positive test result. Right? So the probability of E would be the probability that you receive a positive test result. So what we want to know, though, is what is the probability of H given E? What is the probability that I am sick if I do receive a positive test result? That's what we're after here. If I learn that I have a positive test result, how confident should I be that I'm sick? Now, I shouldn't be guaranteed. No tests are perfect. Any test we take in medicine or wherever, right, there's always a possibility it gives us a positive result even though we actually don't have that condition. Or it might give us a negative result even when we really do have that condition. So just getting a positive result doesn't definitively tell you that, yep, you are sick no matter what. And just getting a negative result doesn't tell you that, yep, you're healthy no matter what. This is why we look at things like false positives and false negatives. We want to know how likely is it that I actually am sick given that I've received this positive result. A similar way to get at this is what is the change between P of H, right, my confidence before the test, and P of H given E, my confidence after the test. If P of H is less than P of H given E, well, that means E has increased my confidence in H. Right? I started off at a low number, and if I afterwards, after conditioning on that evidence, I'm at a higher number, well, that would mean that E has pushed me towards believing in H, right? I am more confident in H than I was before. On the other hand, if I started at a higher number, and then conditioning on the evidence brought me to a lower number, then that would mean E is evidence against H. It's pushing me down. It's pushing me away from believing in H. Let's look at a particular example of how this works. So let's suppose, right, I think there's a 10% chance that I'm sick. And if I am sick, then there's a 95% chance that it says so. If I'm not sick, then there's still an 8% chance that it says so. So just like before, we've been calling P of H our prior, right? This is the confidence we start off with. But we can also give names to these conditional probabilities, right? And this is something we especially do in medicine, but also in plenty of other places like spam detection or whatever. So the probability that you get a positive test, given that you're actually sick, is what we call the true positive rate, right? The idea is that, well, these are the truly positive results. You're actually sick and it's saying so. It's giving you a positive result and it's true that you're actually sick. Whereas we can think of this probability of getting a positive result given that I'm not sick is what we call a false positive, right? It's giving us a positive result. It's telling me that I'm sick, but it's false to do so. This is what we call a false positive rate. So it's actually really important whenever you take a test to be thinking about these rates. Any test that you take is going to have these rates available. No test is just perfect, and so in order to know how good it actually is, they publish exactly these numbers so that you can know how confident you can be based on particular tests. If you've ever taken a pregnancy test and just thought, boom, I must be pregnant based on this one result, right? You're not taking into account the fact that even not pregnant people get positive tests all the time. In order to know how often that is, you want to look at that false positive rate. And in order to know what that really means and how that really affects your confidence, we want to be using this Bayes rule. In this particular case, right, let's think about this in terms of a tree diagram. The idea is we could think about this as the world going in one of two ways, right? There's the world where I'm sick, but there's also the world where I'm not sick. And there's a 10% chance that I'm actually in the world where I am sick, but there's a 90% chance that I'm not actually sick. So there's a 10% chance that I'm sick, but there's a 90% chance that I'm not sick. Next, let's think about what happens when I take the test. If I am sick, then the probability that I get a positive result is 95%, right? That's exactly what this number is telling me up here. If you're actually sick, the probability of seeing this evidence is 95%. And so if the probability that I get a positive result being sick is 95%, then the probability, if I am sick, of getting a negative result is only 5%, right? If I'm sick, there's a 95% chance of getting a positive result, a 5% chance of getting a negative result, right? And seeing it in this tree format hopefully helps you see just kind of like that very conditional nature of this, right? We're saying if you are sick, then there's a 95% chance that you also get a positive result. And if you are sick, then there's a 5% chance you get a negative result. But we can ask these same questions, right, about, well, what if I'm not sick? If I'm not sick, there's still an 8% chance that I get a positive result. And so if I'm not sick, then there would be a 92% chance that I get a negative result. In all of this, these numbers are the ones that I was actually given, and I just used the complement rule to figure out the other numbers, right? If there's a 10% chance that I'm sick, there's a 90% chance that I'm not sick. If there's a 95% chance that I get a positive result, there's a 5% chance that I get a negative result. If there's an 8% chance that I get a positive result, then there's a 92% chance that I get a negative result. And based on this, right, I can then find out, okay, well, then what's the probability of each one of these outcomes happening? So me just sitting out here before I even take the test, I can think, well, there's actually a 9.5% chance that I am sick and the test says so. But there's a 0.5% chance that I'm sick and the test doesn't say so. That's the least likely thing to happen, right? That I'm actually sick, but the test gets it wrong. The most likely thing to happen is that I'm not sick and the test gets it right that I'm not sick, right? That happens 82.8% of the time. Finally, the probability that I'm not sick, but I got told I was sick, is 7.2%. Right, so notice all of these add up to 100%, right? These are the 4 possibilities, just like we were looking at our truth table before, right? These are the 4 possible ways the world could go. I could be sick and get a positive test. I could be sick and get a negative test. I could be not sick but get a positive test. I could be not sick and correctly get a negative test. And these are how confident I should be in each of those outcomes at the start. So just like before, though, when we find out that we actually get a positive result, the idea is we've ruled out 2 of these possible worlds. We get to say, oh, well, it sounds like we know that not E didn't happen. I actually got my positive result. So then what we do is we just say, okay, well then out of this probability pie that's left over, right, how much more likely is one outcome versus the other outcome? Right, I shouldn't be 50-50 between whether I'm sick with the positive result and not sick with the positive result, right? Instead, this one is ever so slightly more likely than the other one. What I should do is I should ask how much more likely. And so just like before, if I'm asking how much more likely is one versus the other, I'm just taking that ratio, right? We're just doing what we did before. We're just taking the total amount and we're just dividing whatever target we're interested in. If I brought 4 slices of pizza to the party and you brought 3 slices of pizza to the party and we wanted to see what percentage of the total amount of pizza did you bring to the party, we would say, okay, take your 3 slices and divide it by the total 3 plus 4 slices, and that would give you the 3 out of 7 slices, and that's the percentage that you've taken to the party. That's all we're doing here. We're just saying, okay, out of what is left over, once we've ruled out not E, we have these 2 things, and so we're just going to add them together, and then we're just going to ask, okay, how much of that belongs to the one? And we can also, right, just as easily, right, if I wanted to see what's the likelihood that not H is true given E, well then I just change the target that I put on top, right? I just ask, okay, what's the probability that I have E and not H given that I know that E is true, right? So I just put my 7.2 on top of the total, and that would give me the about 43%. I went from being 10% confident in H to, once I conditionalize on evidence, to being 57% confident in H. And I went from being 90% confident in not H to being only 43% confident in not H, right? So I am now much more doubtful that I'm actually healthy. I'm much more confident that I'm sick. Now, here's the thing though. I still shouldn't be sure. Right? I still haven't gotten up to, right, like anywhere close to 100% or 90% or anything like that. It's almost still just like a flip of the coin. So the real thing that I should be doing next is just taking another test. And when I take another test, now I can think, okay, I have a new prior to start with. Now I have this 57%. And so now when I get the evidence of my test, it's going to adjust me from a different starting point, and we can keep going from there. So when we're evaluating the quality of the evidence, the question isn't just where did you end up? It's always about where did you start from in relation to where did you end up. If I started at 90% and conditioning on evidence made me 50%, 57% confident as an H, well, now I'm less confident. Now I would say the evidence is evidence against my hypothesis. It's made me less confident in my hypothesis. When it increases that probability, that's when I say this is evidence for that hypothesis. But the whole point of this is you can never answer those questions based on that end answer alone. You always have to ask, where did I start from and where did I go? That's what captures the actual quality of the evidence itself. So each one of these is meant to get us all to the same place, which is just Bayes' rule, also known as Bayes' theorem. And the idea is that whenever we were trying to figure out the probability of some hypothesis given some evidence, we can figure that out using essentially three pieces of information. What's the probability of the hypothesis in the first place, right? What we call our prior. What's the probability that we see this evidence if our hypothesis was right? What we referred to as a true positive rate. And then finally, what is our false positive rate? If our hypothesis was wrong, what is the likelihood of seeing the evidence? So let's look at an example of a Bayes problem. The idea is you're going to be given something like this: a prior, a true positive, and a false positive, right? We start off thinking that, well, we're 80% confident that H is going to happen, or that H is true. The chance that we see E given H would be 0.4, whereas the chance that we see E given not H would be 0.6. So, right, already we can see E is more likely if H was false than if H was true. So if we look to our formula, right, we just have the probability of H times the probability of E given H. And then we have the same thing down here. And then finally we have this third expression here. So let's think about how we fill in each one of these. Well, P of H just is 0.8. And then P of E given H is just 0.4. So we just plug those in on our numerator for those two pieces. And then same thing down below, right? We just have P of H and P of E given not H. And then the only question is this last part. So how do we find out P of not H? Well, that's just our good old-fashioned complement rule, right? If the probability of H was 0.8, then the probability of not H is just 0.2. And then finally, the last piece is just, again, something we're given. The probability of E given not H is just 0.6, so we just plug that in. And what we get is just 0.32 divided by 0.32 plus 0.31, and that equals about 0.73. So how do we think about the evidence in this case? Does the evidence make us more confident or less confident? Well, we can't just look at the final answer. We can't just say, well, that's kind of high. We have to ask, where did we start and where did we go? Because we actually started at a higher point. We started off 80% confident that H would happen, and now we're 73% confident that H would happen. Learning that E happened decreased our confidence that H would happen. This is the point of Bayes' rule. How do you adjust your confidence in a hypothesis based on new evidence in relation to that hypothesis? And really, when you get down to the problems, they can be pretty trivial. Just plugging in the actual values and just turning that crank and getting the answer out. The real question comes down to understanding the intuition behind why does that formula work? What does it mean when we're doing this division? Do you understand the rescaling of the probability in a way that's trying to keep the relationship between the possibilities that haven't been ruled out yet? Hopefully one or more of these explanations were helpful for you in understanding Bayes' rule. This can be confusing the first time you get exposed to it, but the more time you spend with it, the easier it becomes and the more natural you can see it, even in just everyday life. That's it for Bayes' rule, and this culminates what we were after with probability, right? The idea with probability, similar to when we were looking at propositional logic, was how do we change our confidences in things, right? If I start off X amount confident that it's going to rain today, or that this team will win, or that I'll win the lottery, how do I take new evidence and adjust that confidence? How do I say, well, based on these new facts, I used to be this confident, but now I'm that confident. I've brought it up or I've brought it down in a reasonable way. And Bayes' rule is really our way of doing that, our way of saying, well, based on a certain level of evidence, we can change our confidence from this to something new. Okay, take care and stay safe out there.